Hello everyone and welcome to topic number 3 in the OCR computing course. We're looking at binary logic today. Bit of lag in my PowerPoint slide there, but we're looking at binary logic. One of my favourite topics for whatever reason. I think the reason why I like this topic is that it took me personally a while for it to click. When I learnt this, I didn't understand it straight away, and when I did go over it at home and started to learn it for myself, it really clicked and I found it quite satisfying. So what I would say, if you don't understand this topic first time around, don't panic, but obviously if you do understand it, then great, and hopefully I'll get you to understand it at the end. So we're going to look at what binary is. Binary might be an unfamiliar term to you, so if we look at in terms of binary, so our numbering system, the human system that most countries use, obviously in England we use it's difficult to describe because it's not something you ever talk about, but our numbering system actually only uses 10 digits, and we call it, technically, the technical term for it is base 10. It's called a base 10 system. We only ever use the digits 0 to 9. So for the number 15, we're actually only using 1 and 5 digits. We all know that, but it's not something which you would necessarily be taught. In place value, like we did in primary school, that does actually come into binary. We'll look at that in a couple of topics to come. So binary, so even though we don't use one on a daily basis, there are actually many systems, numbering system base 15 called hexadecimal, which we'll look at again in the future. So there are other numbering systems, and one of which is called binary, and this is a base 2 system, meaning that it only consists of 2 digits, 0 and 1. So as opposed to 10 digits, it consists of 2 digits, and computers use these because it symbolises voltage. Everything in a computer is represented in binary form. It makes up pictures, makes up audio, makes up everything you do. The CPU only works with binary. Everything to do with computers is either off or on, because that's how voltage works. That's how a current is. A current can only be off or on. It's like a light bulb. Often the symbol for a light bulb on a light switch is just a straight line and then 0, and that is representing the binary equivalent, which is just 0 and 1. And that is a reason why binary is used in computers. We're going to look at how binary is actually represented, how the computer converts digital data into binary form. We'll look at that in the future. We're not looking at today's video. What we are looking at is binary logic gates. But a little bit of revision maybe for you if you've covered this before, or just an example of what we're going to look at. A bit is simply a binary digit, and it's either 0 or 1, and a byte is 8 bits. So that's how binary looks like when it's used in conjunction with other bits, but we'll look at that in the future. So we're looking at logic gates today, looking at what logic is. Logic is basically Boolean algebra. Boolean is either true or false, as you may have done if you've coded in languages such as Python, or most programming languages, all programming languages will use this, but not all of them refer to it as Boolean. But anyway, the spec doesn't require you to know much about Boolean yet. So logic, I'm talking more about maths and computer science. Test whether a statement or set of statements are true or false, and the Boolean values are true or false, and they're represented by 0s and 1s. So two statements here, 15 plus 12 equals 27. That's obviously true. If you add that up, 27 is actually the answer. That will result in true. If you ran that through a programming language, it would result in true. And this 15 plus 12 equals 29 is false, and we'd represent that with true being 1 and false being 0. And those are the Boolean values, and these are the binary values, and you can sort of use them interchangeably. Just true is 1, false is 0. So there are three logic operations that form the basis of incredibly complex computer systems. So everything in our computer is formed with these 3 different types of operations, and or not. And their functions can be represented by logic gates, which we'll look at in the next couple of slides. We'll look at this is the AND gate, this is the OR gate, and this is the NOT gate. And there are actually 7 standard logic gates. So you've got gates like NAND, NOR, etc., which are combinations of these 3 gates. But fortunately, you won't need to look at them if you plan to do A-level computer science. You will be looking at them, or even university, but fortunately for you, you don't need to look at them now. So let's have a look at the NOT gate first. This is the simplest gate. I'm also going to look at truth tables as well. So this is the symbol for the NOT gate. You've got to memorize this quite a lot of exam questions I've seen actually they give you this symbol, but I wouldn't rely on it. I've seen some exam questions where they don't give this symbol to you, so make sure you learn it. Quite simple, a triangle with a circle, and the role of a NOT gate is to invert the input. So the input is A here, so it reverses the input and outputs the opposite. So yeah, this gate's only got one input, but it's got one output as well. Lots of gates will have multiple inputs, but mainly they only have one output. I can't really think of any examples that have any outputs. So yeah, it basically reverses and does the opposite of what the input is. And the way you would say this is the output is equal to not A. So a truth table, this will make sense in a minute. A truth table lists all of the outputs and the resulting output. Lists all of the inputs and the resulting output from a logic circuit in order to keep track of all possible combinations. So a truth table will basically have a column for all the inputs and a column for an output, and it will list all possible combinations. So here the only two possible combinations are 1 and 0, because we've only got two options here. We're looking at binary true or false, two options and two outputs for each input. So basically, like I say, it does the opposite. So if the input is 1, we're going to get the opposite, which is 0. So if it's true, it's false. If it's false, then it's made true. It basically just does exactly the opposite of your input. Fairly simple, I think. It gets a bit more complicated as we'll look at in the next video, but fairly simple, I think. So slightly more complicated, looking at the AND gate here. So this is the symbol for the AND gate. Make sure you learn this. Sort of like a don't know how you'd really describe it, a half circle with a square sort of extended like that. So this gate has two inputs, or we're going to be dealing with two inputs here, and one output. So this is how you'd write it in a little formula thing like I showed you before. And by the way, out, lots of letters can be used for this and lots of letters can be used for this. This is just my way of representing it. So out for output is equal to A and B. So this is quite complicated, difficult to get a head around a little bit. This for all, so I'll read it to you. If A and B are true, then the output is also true. If not, then the output is false. So a way of interpreting this, or the interpretation of this, is that both inputs must be true in order for there to be an output of true. For any other combination, the output is false. So if you look at the truth table of this, now we have two inputs. We actually have 4 possible combinations of the inputs. And if we apply this to the rule, both inputs must be true in order for the output to be true. So both inputs here are false, and so we must get a false combination. But here we've got one false and one true, but according to the rule, both must be true in order for it to be true. So that's the same for this one. Both of these are false because one of them is false. But here both are true, and that results in both in the output being true. Try and get your head around this. Maybe pause the video, read over what I've written, and look at the truth table. See if it makes sense. And hopefully, yeah, that'll make sense. Just a tip to make sure you get all the combinations. The max you're ever going to get is 4 combinations in this course, because there's only going to be 2 inputs. If you don't understand what I'm about to say, don't worry. I will go over it in a future video. But you can see this actually in binary. This means 0. This means 0. This means 1. This means 2. This means 3. If you don't understand that, don't worry. But that's just a little tip to make sure you get all the combinations. So finally, we're going to look at the OR gate. Again, this is sort of, I don't know how to describe it. It's sort of like a crescent sort of shape, I guess you would say, like a crescent moon. I'm not sure. So again, remember this shape. So the gate has only 2 inputs, A and B, and 1 output. So this is how you'd write it: output equals A or B. So again, for sort of official rule is if either A or B or both are true, then the output is also true, else the output is false. Right, difficult to make sense of what that means. But what it means if you interpret it, if you look over it, it means that if either or both inputs are true, then the output will be true. And if both outputs are false, then the output is false. So yeah, if we look at our truth table for this, you also need to be able to fill in and complete truth tables for simple or not and AND gate and circuits. So here we've got both inputs are false. So if both inputs are false, then the output is false, as we have. But the OR gate is sort of asking if one of them is true, then both are true. And you can see in these two examples, one of the inputs is true, and therefore the output is also true. But here it can also be both. So this would be the same as the AND rule, but we're looking at both. So it will look at the first input, sees that it's true, and it will sort of ignore the second input and just automatically output true. So quite a long video, 10 minutes, just about. Rewatch it if you need to. Do a bit of further reading if you don't understand. But next video I'll be looking at a couple of exam questions where the logic gates are actually combined together into more complex circuits, and that's also part of your course. I didn't want to fit it in this video because it's getting a bit long, and I'm quite tired, spoken quite fast. So yeah, make sure you check out the next video, and yeah, thanks a lot for watching.